Now we'll see B plus tree deletions. So before going to B plus tree deletions, I would like to talk about order of B plus tree. So usually actually B plus tree's order is defined ambiguously. The reason is, so actually B plus tree is proposed by so many people. That means at the same time, so lot of people studied this B plus tree. So one of them is Nath. So Nath defined B plus tree, some other people also defined B plus tree in different ways. One of the, Nath definition is nothing but whatever we are following. We know that. So other definitions are like this. So in Raghu Ramakrishna, if you read this B plus tree, then he defined it with order D. Whenever a B plus tree is order D B plus tree, then he says that whatever the node, whether it is internal node or external node, order is defined like this. So minimum number of keys, the whatever the number of keys you keep in your node should be in between, this one, D to 2D. So that is the way he defined this B plus tree. If that is the case, example, if you follow B plus trees in Raghu Ramakrishna, and especially if it is order 3 B plus tree with respect to Raghu Ramakrishna, then it would be like this. So minimum number of, the keys should be in between 3 to 6. That is the way he defined. So then which one we have to follow is the interesting question, right? In GATE exam, to answer the questions, which one we have to follow? So nothing is specified by this syllabus or anything. So if that is the case, then something we have to follow, and we have to, somehow we should answer it, like we have to figure it out by the options. We don't have options. Sometimes because of ambiguity, multiple options might match, then we can't do anything. So there is one such question, we can't do anything. But so most of the time what we do is what they do is in the exam they mention what is order 3B plus tree. They clearly explain the order definition. If they do that, then we will be happy. Otherwise, we have to struggle whether to use this one or something else. Alright. So somehow we have to resolve it. So what you do is you take all the GATE questions and try to answer them. While answering them, you understand which definition to be used. That is the best thing you can do at this moment. So what I am going to do is I am going to use another variation, for my simplicity. That is, so order 6B plus tree for me now, especially for this problem, whatever I am talking about. So rather than defining order of internal node, order of leaf node, I am defining it in a new way. So what is that is? So minimum number of keys, simply every node should contain 6 by 2. That means half of the keys, like half, 6 by 2 minus 1 keys, and maximum 6 minus 1 keys. That is the way I am defining. Just follow it. So if I use this one, then minimum keys will be 2, maximum is 5. Let's follow this. So in this model, so this is a tree now, right? So whether it is internal node or leaf, so minimum is 2, maximum is 5. Our old definition, if you see our original definition, in that we have two orders, like, so if I say order 6 internal node, what was the idea? So minimum keys you get 2, maximum keys you get 5, same like this. And if I say internal leaf node order 6, then minimum number of keys will be 6 by 2, 3, maximum keys 6, right? So there is a difference. Rather than taking the difference and rather than making things complex, so what I am going to do is I use another definition. So just for this problem, to illustrate the problem, but it's not again standard, don't follow it. Only for this problem you just follow it. Let's say order 6B plus tree for this problem is simply minimum keys are 2. That means I am following internal node concept. In internal node, usually what is the formula? Minimum keys are p by 2 minus 1, 6 by 2 minus 1. Maximum keys are 6 minus 1. I am using that one. So if you do that, so what happens? At this moment it is, see, minimum 2, right? Yes. Maximum 5, we are satisfying. Now we'll understand how to do the deletions in B plus tree. Example, let's say if I delete 8, right? So if I delete 8, then what happens? So this is the place we have to delete it, but minimum condition will be violated. How to tackle it? So what we do is, whenever minimum condition is violated, then we try to take the keys, like a redistribution. We try to take some of the keys from our siblings. So since here this sibling has 2 keys, right? Then we can't ask, because if this sibling gives 1 key to you, let's say somehow, then he will get underflow, right? So that's a problem. Now what to do in this situation? So what we do is we simply merge this is the time to merge two nodes. Let me merge it. If I merge these two nodes, then you get like this. 6, 10, 15, this entire thing is one node, and 25, 30 is another node. Okay. So what is the key for these two? Like, since now we have only two nodes, then something should be removed. Who is that? Guess. So this 10 is unnecessary, right? All these things are going left side. So 20 is left is 6, 10, 15, and 20 is right is 25, 30. Already I told you the purpose of 10 is only helping in anchoring. Then when you don't require it, happily we can delete without bothering about anything, right? So this will be the resultant tree. 6, 10, 15, 25, 30. What if we had here 10, 15, something 18 also, right? Then if the same thing, if we do like, so it was 10, right? Okay, let's keep here something 8. If this is your data like this 10, 20, 6, 8, 10, 15, 18, 25, 30, this is order 6 B plus T, right? In that, if I want to delete 8, what happens? Then we can transfer the keys again. So what we do is, so delete 8 first of all, it is compulsory. Now I send 10 to this side. If I send 10 this side, still I have enough keys, right? The problem is this 10 is unnecessary. We are moving 10 this side. The right anchor will be 15. So we can do this, right? Now again minimum key condition is satisfied. So I can say that again it's like a redistribution. Otherwise, adjusting the keys from siblings, right? So remember it. Now let's take this tree again. Let's try to delete something here. 25. What to do? Whenever 25 is deleted, borrow from your sibling. This is called actually borrow. So borrow from your sibling, but he is already having underflow condition. That means if you remove any key, he will get underflow. Then what to do? Don't take from him. Since 25 is going to be deleted here, we have to move the keys from here to here. But the problem, if you move like that, then again this node is going to have same problem. What is that? Minimum condition violation. So to avoid that, what we have to do is, we have only one solution. We have to merge the nodes. Let's summarize the things. Whenever a node has minimum condition violation, then try to transfer the keys from siblings. So that is called borrowing. If borrowing is not possible, it happens when that node already has minimum number of keys, then you can't move the keys. So at that time, go for merging. So I am explaining you how to do the merging. Simple. This is the idea. Just merge these two nodes and make a node. So if you do that, so you will be forming a node 15, 18, 30. In implementation, it is like you have two blocks, and what we are going to do is, we are merging the blocks. That means all the keys of one block you move to another block and free that block. Just give that block back to your concerned software. What is that? Disk space manager. So he will take care of that. So this is the idea. Now the problem is, here we have two keys, right? Then there are 3 pointers, but you have only 2 nodes. And simply I can say one thing. This 20's purpose was what? To anchor. That means to maintain 2 different nodes. Now there is only one node, then this anchor is unnecessary. So we remove it. So you will have 2 pointers and perfectly it will match you. See, 15's left is 6, 10, 15's right 15, 18, 30, and maximum keys are 5, satisfying. Minimum keys 2. Now let's continue this deletion process. Let me delete one more node. Let's say that is 10. If I delete 10, so again minimum condition will be violated. If I delete 10, so what to do? Transfer the keys. Borrowing. If I borrow, so what I will be borrowing is 15. So I will send 15 this side, but this should not be the anchor. The right anchor is the next element in this resulting node, which is nothing but 18. Otherwise, the least number from this node. Now same story. Let me delete 18 this time. If I delete 18, again you violate minimum keys condition. I can't take the borrow. The problem, even that node is suffering from that. Then go for merging. If I merge, then what is the idea? So it will be like this. Blindly merge it first of all. 6, 15, 30. This entire thing is one node. So this entire thing is one node. But to have one node in your in your lower level, the higher level should contain how many keys? 0. When a node contains 0 nodes, then only you can have one pointer. I can say like this. But whenever a node has 0 keys, we can delete it. So finally, whenever you have only one node, then the root level, that I mean otherwise the next level which you have, that should be deleted. So this is the idea. Now delete again 6, happily we can delete, no problem. Delete 15, simply delete it. Sir, but minimum condition is violated. So this is root. Root doesn't have any minimum condition. That was the reason why we say root doesn't have any condition. Then only we can maintain the tree. Otherwise, always, in this kind of border cases, you can't maintain the tree. Understand? Similarly in insertion also. So this is about deletions in B plus tree. Let's take one more example and try to do the same, so that we get the experience. Now we'll see one more example of B plus tree and how to do the deletions. Okay, so I would like to tell you one point. Here we always delete the key from the leaf. We never need a situation where we delete a value from the internal node. The reason, usually what you do, actually we delete from the file, correct? So whenever you delete some data from the file, then we have to delete that file's key value should be removed from your B plus tree. And we know that that file's key value will be always in the leaf level. That's why we did it from the leaf level. But when it comes to B tree, you will have all the cases, like sometimes you might need to delete from the leaf node, sometimes you want to delete from the internal nodes also, because everywhere you have record pointers. Here we have only records and their pointers in leaves. That's why usually your always deletions begins with deletion of leaves. Okay, so now the question is, how to delete something like 87. So case number 1. What is case number 1 is, whenever your leaf has less than minimum number of keys, what to do? Then always we try to, so rule number 1, asking the neighbors, correct? So that is called borrowing. Let's do the borrowing process. If borrowing doesn't work, then go for merging. Two things you remember, okay? So 85 here, 95 can be borrowed. But if I move 95, we should be careful. The anchor should be proper. Remove this 90 and keep appropriate anchor, which is nothing but least value in this node, 100. Done. Now again we try to understand deleting 95. If I delete 95, again insufficient keys in this one, then ask neighbor number 1, anyone, sibling number 1. So he is having minimum number of keys. Then ask this sibling, he also has minimum number of keys, so we can't try this borrowing. Then what to do? Go for merging. Either you merge these two or these two, it's up to you. So let's merge these two. Whenever I merge these two, it becomes 85 and 100, 120. Then whenever you merge two nodes, then here you don't require this anchor, correct? We have only one. So that's why we remove it. Now see, 8 is left, 8 is right. Cool, right? Now we'll see this node. In this node, again minimum condition is violated, correct? We have to take care of that. So whenever you get a violation at internal node, then what to do? Same process we apply. So go for borrowing. So in borrowing, we try to move this 40 key to this side. And I want to say one thing here. We can, example, you have lot of keys in this node, let's say, then we can move multiple keys also. So I teach you how to move 40, but what I want to say is, you can move 35, 40 also, but at this moment we can't do even moving 40. The reason, if I move 40 to this side, then this internal node will have same problem. Whenever some internal node has that minimum condition violation, then we should not go for borrowing. What is the second strategy? Whenever borrowing doesn't work, then we should go for merging. Let me merge these two trees. So if I merge these two trees, then it will become 35, 40, 80. Simple, like this. Whenever you merge two nodes, then anchor should be removed. Then only it will match. Then only this node will match number of nodes, a number of children. Correct? We have only 2 children. Then only one key should be sufficient. Correct? So we can remove this pointer. Now so far see, 35, 40, 80 are merged. 35 is left, in between 35, 40, no problem, 40 is right, this is 8 is left, this is 8 is right, it's perfect. But the only problem is, now from root you deleted one key, right? Then root is violating this minimum key violation, correct? But already I told you, root doesn't have any such condition, that's why we can stop it. Here one important thing you should notice is, when you have 3 keys, how many pointers we can have? Only 4. Then only that will be search key. It's search tree, right? 1, 2, 3, 4, 5. We have 5 children with 3 anchors. We can't properly anchor them. That's why we need one more key. That's why whenever you delete a node, whenever you do internal nodes merge, then the anchor should be pulled to this level. So it was 50, right? You add it. Now see, if you do that, then this anchor is going to help you in properly adjusting the tree. See, 35 is left, perfect. It is proper, right? 40 50, in between 40 50 now we have 40 45, perfect. Between 50 80 we have 75 77, perfect. 8 is right, is 85 100 120. In that way we can understand. Now we keep deleting. So root doesn't have any problem, right? Yes, we know that. Now we try to delete one more key, which is, let's say, 77. If I delete 77, is there any problem? Yes, minimum condition got violated. Then we have to get the keys from siblings. We have two siblings, right? So with respect to 50, these two are the siblings. With respect to 80, these two are the siblings. But this right sibling has enough keys. We try to move. Then 85 will be moved. Then there is no problem from right side, but anchor should be removed. Proper anchor we have to keep. So what is the proper anchor? 100. Yes, successful. Now we keep deleting. So this time 75. If I delete 75, borrow from your left sibling, not possible. Borrow from right sibling, not possible. Already they have only necessary keys. Then we have to do the merging, right? So if I do merging 85 100 120, otherwise you can merge with 40 45 also. Let me do merging with right side thing. So it is not compulsory. Then 85 100 120. So whenever you merge two leaf nodes, then anchor should be removed, right? You don't require to pull it up. So finally 85 100 120 is one node. Then see, three keys, 1 2 3 4 children, perfect, right? So this is about deletions, right? We still continue so that we get confidence, right? So we try to delete one more value, which is, let's say, 45. If I delete 45, then same thing, insufficient keys here. Then borrow from here, not possible. Borrow from right sibling, yes, it is possible. Then 85 will be moved this side. Then anchor should be right. What is that? 100, right? 100's left is 40 85, and 100's right is 100 120. Now one more time, let's delete 85. If I delete 85, then what happens? Minimum key violation here. Left sibling doesn't have sufficient keys to give. Then right sibling doesn't have sufficient keys. Then go for merging. If I merge with right, then it will be 40 100 120. So if I delete, if I merge 40 100 120, then this cannot be the right anchor, right? And so we don't require anchor also, right? Because we have only three children, two keys. Always you remember, whenever you merge leaves, then anchor to be deleted. That is the one difference between BT deletions and B plus T deletions. One thing you remember, whenever we merge leaves, then simply delete the anchor. That is what we learned, right? Now we still delete some more values to get confidence. Let's delete 39. If I delete 39, so left subtree, of course sibling. So this left sibling doesn't have sufficient keys, right sibling has sufficient keys, then 40 has to be moved, correct? So if I move 40, then this should be removed from here, but this 40 cannot be the right anchor now, the right anchor is 100, right? Now same thing. Now let's delete one more, let's say something 35. If I delete 35, then the problem is left node doesn't have sufficient keys, right node doesn't have sufficient keys, then only thing is merging. Either you merge these two or merge these two. So whenever you merge these two leaves, then 40 100 120, right? Let's write here 40 100 120 are merged, then anchor to be deleted. So 35's right is 40 100 120, 35's left is 32 33. But again problem is at now internal node. So internal node is violating minimum key condition, then story begins again. So first borrowing. To get borrowing, we don't have sufficient keys in left subtree, right? This left node. Then what to do? Only thing we can do is merging, right? So simply we merge. I'm merging now 20 26. Whenever you merge these two internal nodes, then we have to take the, otherwise we have to pull the anchor. So when you pull that anchor, then now the current root doesn't have anything. So 20 26 30 35. If you do that, you get 1 2 3 4 5 pointers. See the children. So 1 2 3 as it is, see 20 is left as it is, 10 15 20 26 in between, this one as it is, 26 right, and this one is C. This is 26 right, correct? 30 is left, perfect. Now this is in between 30 and 35, perfect. It is 35 is left and 30 is right. Now similarly, that's why that anchor is really helpful for us, right? 35 is right will be same thing, 40, 100, 120. In that way you can understand, lot of deletions, right? We have to cover only one case, that is, sir, when this node, whenever you delete from internal node, let's say that violates this minimum condition, then we were always merging, right? But that is not compulsory. Before that we should go for borrowing, right? We will see that case. We missed it because of this structure. We never got that case. Always whenever I was deleting from this internal node, that means whenever that internal node has insufficient keys, then at the same time left subtree also having minimum nodes, that's why minimum keys, so that's why we were not able to do that. But we have to do that borrowing process. Of course that's easy, it's not a big deal. That borrowing process we should do whenever we have sufficient keys at left side or right side, whatever, in any internal node. We'll do that specially for one tree now. Okay, now we'll see this case. So example, let's say you are deleting 42. If 42 is deleted, always we start from leaf first of all, right? So only we have right sibling. The right sibling doesn't have enough keys, then we have to go for merging. Let me do merging first. So when you do merging, we know that whenever leaves are merged, we have to delete this anchor, correct? So 50 will be deleted, right? So it would become 44, 52, 54. Let's add them. 44, 52, 54. Now there is only one key and two nodes. At this moment in this lower level it's okay, but 55 is only one key, but minimum condition is 2, right? Then what to do? Then go for borrowing. Now this is insufficient keys at internal node. Then step number 1, go for borrowing. If borrowing doesn't work, then go for merging. Now we have left subtree in this, for this internal node, left subtree, it has sufficient keys, right? More than that, then we can adjust. So the adjusting process will be like this. This 35 should go here, and because we have to push through, that means that moving should be like this. We have to push this 35 here, so 40 should come this side, then only it will work. Because see, 40 is anchor, right? 40 is maintaining this condition. 40's left side is this one, 40's right is this one. If you simply move 35 and its children, then you have a problem, correct? You will get a problem. That's why we have to move that things through the root, otherwise through the at this moment in this problem we have to move the keys through the parent, I can say. So let me move through the parent. 35, please go to 40's place. 40, come to this point. So this is the way. So we can move one key, and remember one thing, we can move multiple keys also. That means once you move 35, we can move 30 also if you want. That means this process generally can move multiple keys, but let's confine ourselves to only one key first. So if I move 35 this side, then so here you see we have 25, 30, correct? But how many children we have? 1, 2, 3. This child has to be moved, remember it. That means this pointer should be moved here, correct? But so what happens to this one, sir? We have 40, 55, right? There are 3 positions. 40 is left like this. In between 40, 55, this one, and here this one. That's it. Cool. So finally this is the answer, right? Perfectly it works. 35 is left, 30. And 30 is right. 30 is right is 32, 34, correct. 35 is right is this one, 36, 38. Perfectly correct. Now we'll see one more time. So this time, of course, this time it won't work because this time we don't get same problem, right? The reason, if I delete 36, then insufficient keys, we will merge leaves. If you merge leaves, anchor will be deleted. Then internal node will have sufficiency problem. Then we go for borrowing, but that did not work, correct? That won't work. Then we have to merge these two. So of course that idea we know, right? Let's summarize the things now. Step number 1, always we start deleting at leaf. If leaf has, after deleting also, if leaf has sufficient keys, happy. If leaf doesn't have sufficient keys, then we have to merge with left sibling, otherwise right sibling. If they have sufficient keys, if they don't have sufficient keys, then go for merging, right? So that is the one thing, either borrowing, otherwise merging. Now when you merge, what can happen is, borrowing is cool idea, so it will stop there. But if you do merging, whenever you do merge leaves, then you are deleting the anchor, right? So that is like deleting from internal node. Then if deletion at internal node happens, then how to delete? If after deleting it, then we have to go for borrowing if it is possible. If borrowing is not possible, again we have to merge internal nodes. That's it. Keep practicing. Take one example and whatever I explain, right? You just follow them and try to get some experience. Then only you can answer. And one more thing, in GATE exam generally they can't ask more questions from here. The problem, they have to give very big tree and there is no one unique procedure. These are all practices in the implementations. I can say that there are multiple ways we can delete the keys. That's a problem. This is one of the algorithm. There might be other algorithms possible, right? If that is the case, then how can they ask a unique question or unambiguous question? They can't ask. Understand? That's why so far there is no question from deletions. If you see in previous GATE questions, if they ask any deletion question, please follow this procedure. Okay, now we'll see some of the important informations about this B plus tree. One thing is, you are in B plus tree, all the leaves are connected like this, either one way or two ways. So actually one way is sufficient, but we can connect through two ways also. So why one way sufficient, I will tell you. What is the purpose of connecting? Since your leaves contains all the information about records, right? That means every record pointer is stored in leaves. That's why. So if you connect these leaves, so automatically, because it is search tree, then that, I mean, if you connect them, it will form ascending order of keys. Okay. So I assume that, let's say here we have record pointers. Then if you search for some value, like example you are searching for 13, then once you get it because of search process, then after that, if you want to know all the records whose key value greater than or equal to 13, which will be easy, for that you don't require again search for 19 separately, 20 separately, 24. You start here and simply scan all the blocks which are connected now, see. Then 13, take the record pointer. Next 19, take the record pointer. Come here, take the record pointer, take the record pointer. In that way, if you take all the record pointers and if you go to the records, then every record of your data can be scanned contiguously, otherwise in ascending order. That's why, example, your query is asking this question, that is of course known as range query. Example, your query is like this. This is, let's say, this is collection of salaries. Select all the information from your table employee. This is employee table, and let's say index on salary. These are all salaries. Then from employee, where employee dot salary, e dot salary greater than or equal to something 24. If this is your query, so this is called range query. So range queries can be very efficient in B plus tree. Simply first search for 24, you get here, right? You take this record and simply take this right pointer like this, I mean next pointer. You come here and fetch it, fetch it, fetch it, fetch it. That's it. You are fetching all the records. You never miss any record. But in B tree, if you do the same thing, you can't get, because your B tree structure will be like this. Some of the records are in internal nodes. So if you connect the leaves also, you can't get all the records. Example 20, 25. So this is your B tree structure. Something 10, 15, something here 22, something 24, 26, 28. Example. Then you are searching for example, same thing, you want to know all the records which are greater than or equal to 24. Then search ends here, you get it. After that, see, one record 25 is also one of the valid record pointer, right, at 25. So we have to take the record pointer from here and here and here. So without searching entire tree, you can't get them clearly, right? So that's why what I want to say is, there is a subtle difference between, otherwise major difference between these two. B trees, though you connect them, you can't answer range query easily. But if in B plus tree, if leaves are connected, then happily and very effectively we can answer range queries. That is one of the greatest advantage of B plus tree over any indexing. So far we have seen primary indexing, clustering indexing, everything, right? So B plus tree has in all the tree indexings. Let's confine ourselves to tree indexings. In entire tree indexings, definitely this B plus tree has advantage, right? So one more thing. Since your internal node has more number of keys and more number of tree pointers, I mean if you compare with B trees, so if you take B tree and B plus tree with same block size in your computer, then automatically your internal node of B plus tree will be more packed. That means it will be packed more than this B tree. So your B tree contains, let's say, some 1 2 3 4 5 6 pointers at root. Then same B plus tree, in that B plus tree we are not maintaining record pointers, right? Because of that, number of keys we can store more. Because of that, you will have more pointers here. Sir, I will also have more pointers here. Whatever the pointers you will have here for same block structure, I can keep more pointers here. So B plus tree will be definitely will have more pointers than B tree in the starting level. When initially the starting level has more pointers, then further nodes which are pointed by these pointers will have again more pointers in that way. So quickly your B plus tree will grow if you compare with B tree. That's the reason. So your B plus tree requires less number of levels if you compare with B tree to index same file. Example, your file F is indexed by B tree with 10 levels. For same terms and conditions, that B plus tree might take only 6 levels or 4 levels. So the advantage is, number of, because in the searching process we search level by level, right? So less number of levels, less disk transfers, but it's not greatest advantage. Why? In B tree your keys are distributed over all the places. That means sometimes if your fate is good, then you get the data at root, then only one block transfer. Let's compare. Example, this is your B tree, this is your B plus tree. In B tree, let's say you have 10 levels, but in B plus tree we know that it will be lesser number, lesser number than 10. It's, let's take 5 levels. Now always B plus tree takes only 5 levels, exactly 5 levels to get the data. The reason, your records are all in leaf, right? So finally we have to come to the leaf. Further, definitely all these 5 levels whatever to be traversed, correct? So we have to descend the tree up to these many levels, but here it is not compulsory. Example, in root there is a key called 10 and you are searching for 10, then your search stops there and you get the record pointer because we have record pointers, correct? So finally, that's why B tree, if your fate is good, one block transfer is enough to search. If in B plus tree, then always 5 block transfers. But in the worst case, since you have 10 levels, if your data is at leaf, then it requires 10 block transfer. See, it's highly variable. 1 block transfer to 10 block transfers approximately. Here it will be always 5 block transfers. So example, in hard real time system. So there is some hard real time system means, example, let's say some pilot is riding the flight and this pilot is going to, this is pilot. So this pilot is going to take the decision based on your database query. So whenever he is in a critical situation, he is connected to some database. So through database, he is going to get the information to drive it. Okay. So if that pilot uses B tree, then what happens? Sometimes he will get very quick answer, but sometimes it's very long. That means it's highly variable. But in B plus tree, always we can believe that after some time you definitely get it, right? So that's why whenever you have that kind of strong and stringent requirement that within time limits I want answer, then go for B plus tree. You mean this variation is okay for you. Sometimes you want quick data, then you can go for B tree. Apart from that, B plus tree has one more greatest advantage, that is, they here range queries are so efficient. So in your real time, so people write lot of range queries like employee salary greater than 1000, less than 1000, in between 500 to 1000. Everything will be effective here in B plus tree. And other indices, like there is one more indexing technique called hashing. Hashing also will be awkward. That means hashing will not have efficiency when it is searching for range queries. That means whenever there is a range query, to index it through index, if you want to answer, definitely best way is B plus tree. So hashing also cannot have that kind of advantage. What is the reason? What is hashing model? So we take, your data will be stored in some buckets. We know the rough idea about hashing, right? In buckets. So example, let's say you are searching for a value 50, then it will fall under some bucket and will go there and there will be a record pointer and we'll get it. Now if you want to know all the records which are less than or equal to 50, then this method will not work, because we don't know what about, we don't know about the bucket numbers where the records with less than 50 values reside. But in B plus tree we have that advantage. If you search for 50, other things will be easy, which are less than or equal to 50 or greater than 50. So hashing, otherwise B tree, they don't have this kind of advantage. That is what I would like to say about B plus tree. Okay. So finally, so I say B plus tree, we in implementations majority of the systems use this B plus tree, or otherwise the hybrid version of B plus tree and some extra things. But definitely we can go for B plus tree over B tree.